Standard input-output operations. Character input. The simplest input mechanism is to read one character at a time from the standard input, normally the keyboard with getChar. Character output. If the fundamental output mechanism in C put char, put the character on the standard output device, which by default is the screen. Then we see formatted input and outputs. Formatted input and output are closest to the facilities offered by Pascal or Fortran, and usually the easiest to use for input and output. The versions offered under C are little more detailed, offering precise control of layout. Formatted input. Scanf allows formatted reading of data from the keyboard. Like printf, it has a control string followed by the list of items to be read. However, scanf wants to know the address of the items to be read. Formatted output. Printf formats the given argument according to the format string and writes them to the standard output. Line input. Gets function used to read a line of characters without dividing the line into individual words. Line output. Writes a string to the output and follows it with a new line character. Implementing C designs in hardware. A full-featured ANSI-C to synthesizable RTL Verilog compiler was used to implement several system-level algorithms in hardware. These designs were created in C and compiled into RTL Verilog. Impressive results were achieved for designs ranging from encryption, compression, and sorting algorithms to prime number generation and FIR field algorithms. ANSI-C is an ideal choice for high-level systems behavioral design since it is familiar to the majority of system engineers. Encryption, filter, compression, prime number, and sorting C algorithms have been implemented in hardware using a compiler, conventional logic synthesis, and FPGA products. Although these examples have very sequential data flows, competitive execution speeds were obtained using hardware implementation versus software execution on high-performed Pentium Pro PC systems. Larger performance gains are possible for more parallel algorithms using simple and less expensive hardware implementation. Thus, this design methodology improves the productivity of system architects as well as experienced hardware designers. This image shows simple structure Verilog template instantiating RTL Verilog module compiled from the LZWC code for implementation in APS-84 FPGA hardware. This hierarchical structure allows other external memory and arithmetic macro modules to be added if desired. The FPGA input-output signal pin assigned to the PC interface and external SRAM memory are defined within this top hierarchical module.
Let's go to the industrial end of the scale, and I'd like to call up Greg Bilella, DE from Sun, and he's been working with a large crowd of people to get this ABB robot to do something other than self-destruct.
Hey James, see ya.
Yeah.
All right, so I want to take you over here and introduce you to Poindexter, or
Poindexter, huh?
Right. This is the world's fastest industrial robot. It can accelerate at 10 Gs. That means this end effector will go from 0 to 280 miles an hour in a second. This is not a toy.
Yeah. Now we're not actually doing that today.
No, we're not doing that today. This is
we have you know like really wimpy power supplies attached on this thing. It has a high coefficient of lethality, so we had to be careful at the show.
Now we consider about the Java programming language. Java program class files provide bytecode instructions to Java virtual machines programs that run on conventional processors. However, there is no reason a Java real machine that processes bytecodes directly in hardware cannot be built, and in fact several have been. Sun Microsystems initially proved the concept in the late 1990s with its Pico Java chip. Since several independent Java hardware implementations have hit the market. The JVM specification requires a stack-based processing scheme rather than the register approach common in conventional hardware. The language designers wanted Java to run on a wide range of processors, including simple embedded types that had few registers, and so decided the stack approach was the most portable. Java processors cover a wide range of design purposes. A standalone Java chip design provides all the capabilities needed to act as a general-purpose computer. The processor executes the bytecodes directly. Most of the current processors only execute a subset of the full Java instruction set. For example, a chip might leave out the floating point instructions since for many applications, such as a microcontroller, floating point instructions are not needed. Another approach is to add a Java coprocessor to a conventional processor. The Java coprocessor in some designs translates the bytecodes into the instruction set of the conventional processor and accelerates the running of Java programs. In more of a companion processor approach, the Java hardware takes over the execution of Java bytecodes completely whenever a Java program runs, while the operating system and other types of non-Java code run separately in the conventional processor. Java boards. A number of Java boards level systems are available today. These include boards that provide more or less complete computer system, while other boards plug into the companion slots of carrier cards like in Photo, which in turn provide various types of hardware such as Ethernet, digital to analog converter, analog to digital converter, etc. that are controlled by the processor. The figure shows two such boards. The IMSYS CJIP processor comes with their SNAP SIMM card and is shown here plugged into a Systronic socket board. The other board holds the Parallax Javelin stamp and includes a breadboard for experimenting with circuits controlled by the Javelin. Both boards include serial ports for input-output.
Right. So what we're doing is we're going to draw the picture we took of you on the show floor, and you probably all saw it out there. We did a lot of pictures. It's running about half speed now. It's made by ABB in Sweden. You got that one. And so a couple things about this. This is kind of a world's first here. This is the first Java-powered industrial robot.
Right. So
Can I say that again?
So Java is actually swinging the voltage levels.
That's right. This is actually the folks at Lund University who helped us a lot with this. Did a lot of the work. This is actually the feedback control. So we are actually reading the position of these motors up here every millisecond, giving them commands, computing the next position 1,000 times a second. And you can't miss. If you miss, this thing will hurt itself. It'll hurt James, it'll hurt me, we'll have carbon fiber all over.